Hello everyone, I am Deepak Shah from Batch 36 AI. Today I am presenting my big data programming project, Nepal Bus Transport Predictive Analytics Platform. This project addresses a critical challenge in Kathmandu Valley, unpredictable bus delays that affect thousands of commuters daily. Over the next 8 minutes, I'll walk you through the problem, my solution, and the machine learning models I built and the results achieved. Let's start with the problem. Kathmandu Valley's public transport system serves over 5 lakh passengers daily across dozens of routes. However, the system suffers from chronic unreliability. Passengers don't know when their bus will actually arrive. Transport authorities struggle to optimize schedules. The challenges are unique to Nepal. Narrow, ancient road, frequent festival disruptions like Dasai and Tihar, monsoon, weather impacts, and limited real-time tracking technology. Traditional scheduling systems simply can't account for these dynamic factors. Can we use data science to predict bus delays before they happen? Can we identify patterns that help authorities make better decisions? So, moving on. So, what's the solution to all of these problems? My solution is a comprehensive predictive analytics platform with 5 key components. So first is data collection. I created realistic datasets covering 8 major Kathmandu routes operated by 5 companies including Saja Yatayat and Metro Bus. This includes 20,000 total records, bus timetables, GPS location tracking, traffic disruptions and historical delay patterns. Second, data storage. I built a SQLite database with a normalized relation schema, ensuring efficient query and data integrity. Third, machine learning. I trained two models, a random forest classifier to predict delay categories and a gradient boosting regressor to predict exact delay minutes. 4. Analytics. The system identifies peak hour patterns, weather impacts, and problematic routes. Fifth, visualization. An interactive streamlit dashboard allows stakeholders to explore insights through intuitive charts and metrics. Let me dive deeper into each component. For data collection, I generated 4 realistic data sets based on actual Kathmandu transport patterns. The timetable dataset contains 5,000 service records with operator route like Ratnapar to Kalanki, schedule times and frequencies. The location dataset has 8,000 GPS tracking records with coordinates, vehicle speed and passenger counts. The disruption dataset includes 1,500 incidents, traffic jam, road construction, accident, strikes, and festival events, each with severity ratings. The delay dataset in my main training data 6,000 historical records showing actual delays with contextual factors like weather, peak hours, and traffic density. I pre I pre-processed this data carefully, handling missing values, standardizing formats, removing outliers like impossible speed readings, and validating GPS coordinates to ensure they are actually within Kathmandu Valley. The data generation incorporated realistic correlations. Peak hours have 40% higher delays, rain increased delays by 60 to 80%, and longer routes naturally accumulate more delays. Now moving on, I built two complementary models. One is random forest classifier for delay categories. This predicts whether a bus will be on time, have a minor delay under 15 minutes, moderate delay under 30 minutes, or a major delay over 30 minutes. So why random forest? It It handles mixed data types well and is resistant to overfitting through ensemble averaging of 100 decision trees and provides interpretable feature importance. I achieved 87.3% accuracy with balanced precision and recall across all categories. So now Model 2 is a gradient boosting regressor for exact delay prediction. This tells you specifically how many minutes late the bus will be. So why gradient boosting? It is sequential learning corrects error from previous trees, making it ideal for precise numerical prediction. I achieved a mean absolute error of just 4.2 minutes, meaning on average prediction are within 4 minutes of actual delay. The R-squared score of 0.83 means the model explains 83% of delays variance. Both models used 7 features: peak hour indicator, weather conflict, weather condition, traffic density, scheduled hour, route distance, whether it is a weekend, and scheduled duration. I split data 80 to 20 for training and testing and used five-fold cross-validation to ensure the models generalize well. The most important predicators: peak hour had 28% importance, weather 22, and traffic density 19. This makes intuitive sense. Rush hour, traffic, rain, and congestion are exactly what we would expect to casual delays. Now for the key finding part. The analysis revealed several actionable insights. Finding 1: peak hour matters enormously. Morning rush from 8 to 10 am experiences 22 minutes average delay. That's 45% higher than off-peak. Evening rush from 5 to 7 p.m. is even worse, 26 minutes average. It's 68% higher than off-peak. Midday between 11 and 3 is the most reliable time with only 8.7 minutes average delay. Finding 2: weather impact. So, weather has significant impact. Clear weather gives us a baseline of 12.5 minutes delay. Fog increases this by 34% to nearly 17 minutes. Rain increases delays by 68% to over 21 minutes. When you combine peak hours and rain, you are looking at 35 plus minute delays. Now finding 3: route performance varies dramatically. The biggest route is the best route is Tripureshwar to Maitigarh, just 3.5 kilometers with 8.2 minutes average delay. The worst is Baneswar to Bhaktapur, 15.7 kilometers with 25.8 minutes average delay. Finding 4: disruption analysis shows traffic jams are most frequent, 450 cases, but strikes and bandhas through rare at 120 cases have the highest impact at 45 minutes average delay. Finding 5: operator comparison revealed Saja Yatayat has the best performance with 78% on-time rate and 11.2 minutes average delay, while Valley Transport struggles with 19.8 minutes average delay. To make these insights accessible, I built an interactive dashboard using Streamlit and Plotly. Let me show you the 4 main sections. The Overview tab displays real-time metrics like total routes, average delay, on-time percentage, and active disruptions. Below are interactive charts showing delay distribution, hourly patterns, and weather impacts. You can hover over any data point for exact values, zoom in on period tabs, and pan across the data. So you can do like this, and it will show you like how it's impacting the average delay. So here we can see fog delay 16.8 minutes, rain 21.3, and clear is 12.5. Here we can see by time, and there is a pie chart of it. Now moving on, the route tab. So route tab ranks all routes by performance with color coded bars: green for good, yellow for fair, red for poor. The detailed table use gradient coloring so you can instantly spot problem problem areas. Select any route from drop-down to see specific statistics. The Disruptions tab compares disruptions type by both frequency and impact using dual charts. The pie chart shows severity distribution, and the table lists recent incidents with their resolution status. So this one is for the route. We can see the average delay, Old Bus Park to Koteshwar, and here are some routes. Here are the average delays and statuses. And this is the disruptions. So average delay, red one is average delay, and here is the frequency. We can see here traffic jam occurrences 450 average and the average impact of it, road construction, their occurrence, average impact, festival and events, their occurrence and average impact. So we have traffic jam, road construction, so frequency this, and frequency is like 220, and the average delay impact is 15, so it's something like accident, vehicle breakdown, strike slash blunders. So now moving on to prediction. The prediction tab showcases model performance with accuracy metrics, precision recall table, and feature importance visualization. There is even an interactive widget where you can test predictions, select an hour, weather condition, and traffic label, and instantly see what delay the model predicts. Everything updates automatically from the database, and Streamlit's catching make, makes it responsive even with a large dataset. We got so so now moving on to key challenges and solutions. So now challenge 1, data scarcity. There is no comprehensive open dataset for Nepal bus transport. Solution: I generated realistic synthetic data grounded in actual Kathmandu geography, route names and traffic patterns. While this has limitations, the data passes plausibly checks and informal validation with transport planners. Now my challenge 2, class imbalance. My data set had 41% on-time buses but only 8 major delays, causing the initial model to just predict everything as on time. Solution: I used random forest class width parameters to penalize majority class errors, improving minority class recall from 58% to 81%. Challenge Challenge 3, Dashboard Framework Selection. I initially planned to use React, but it required Node.js, JavaScript knowledge and complex setup. Solution: I pivoted to Streamlit, a Python narrative frame. This reduced development time by 60% and maintained full interactive while leveraging my existing Python skill. These challenges taught me adaptability and practical problem solving under constraint. So, so now the question remains, what's the potential impact if this system could be deployed? And the answer is, if deployed, this system could reduce average commute times by 10 to 15% through predictive dynamic routing, improve on time performance from current 60% to a target 75%, enable proactive passenger alerts when major delays are predicted, guide data-driven infrastructure investment in problematic routes. For future work, short-term goals include partnering with Saja Yatayat for real-world data piloting, aiding automated SMS alerts, and incorporating Nepali festival calendars as features. Midterm, I'd migrate to a streaming architecture with Apache Kafka for real-time prediction and expand to other cities like Pokhara. Long-term vision includes integration with traffic signal systems and carbon emission modeling. This methodology is transferable to other South Asian cities facing similar challenges, potentially benefiting millions of commuters. To conclude, I successfully built a comprehensive predictive analytics platform achieving 65.83% delay classification accuracy and 4.2 minutes prediction error. The system integrates data collection, storage, machine learning, and interactive visualization into a cohesive solution. This project demonstrates that even with modest datasets, appropriate machine learning techniques can yield operational useful prediction for smart city applications. It proves that students can tackle real-world urban challenges and deliver solutions that matters. The experience taught me that effective data science requires not just technical skills but also domain expertise, ethical reasoning, communication abilities, and adaptability when faced with constraint. I am grateful to my supervisor, Mr. Siddharth Nipani, for his guidance through this project. Thank you for your attention. I am happy to answer any questions. Thank you.